This is a demonstration of the AquaModel plugin for the easy environmental analysis system AquaModel software. Easy is a flexible GIS, or Geographic Information System, application with a number of tools for data handling, analysis, and visualization. It includes a range of model extensions which we call plugin modules to the Easy software system. AquaModel is one such plugin module of Easy. It utilizes readily available environmental data from field measurements and databases, including remote sensing and satellite imagery, to model a real-time, three-dimensional simulation of the growth and metabolic activity of aquaculture fish, as well as the associated flow and transformation of nutrients, oxygen, and particulate wastes in adjacent waters and sediments. Dedicated validation and tuning studies have been completed at a number of temperate and tropical areas worldwide, and it is currently in use or has been used by organizations in the United States, Canada, Chile, Hong Kong, the United Arab Emirates, and Oman, among others. AquaModel is a relatively simple, yet very powerful program to use, and we have led many training sessions to train other users in the operation of AquaModel and Easy. Here, we have developed a demonstration AquaModel project in Chile. This project includes coastline and bathymetry of the Chiloé Bay region. Easy includes a range of GIS tools. For example, in the bottom right-hand corner of the screen, we can see the latitude and longitude of the cursor as we move it about the screen. By control-clicking at any location, we can see the data value of the underlying imagery, in this case, bathymetry. By holding down Shift and clicking and dragging the cursor, the user can also move a transect that gives the distance of the drawn line, as well as its header. The transect also affects the image profile plot shown at left, which displays a plot of imagery values along the length of the transect. AquaModel can also display coastline data from multiple sources, including World Data Bank, World Vector Shoreline, ArcShape, and even user-created text files. AquaModel can also utilize detailed bathymetry to define the depth of the water column. If no bathymetry data is available, AquaModel allows the user to specify a single depth for the entire simulation area. We will now zoom into a simulated fish farm that we have added to the project. This farm includes 2 clusters of 14 net pens each, shown as black dots, as well as multiple capture cells, shown as gray dots. The green box around the pens represents the boundary of the modeled array. This array is a 3-dimensional set of boxes full of simulated water. Water, nutrients, and waste flow through these boxes at every time step of the simulation. Fecal and feed wastes leave the pens and sink to the bottom based on bathymetry and current flows, and are deposited and resuspended based on specified benthic parameters. Current flows can either be based on 2D single-point datasets such as output from an ADCP current meter, or can use 3D circulation models including FVCOM, ROMS, and various forms of Delft, providing a basis for analyzing the effects of convergent and divergent current flows as well as eddy circulation. In this example, the simulation uses a 2D single-point time series of current velocity and heading at various depths. These gray capture cells, with locations determined by the user, output a range of data to an external CSV file, which can then be used for external analyses. Available capture cell output includes current velocity and heading, water, oxygen, nitrogen, phytoplankton, zooplankton, suspended fecal, feed, and oxygen, and a variety of benthic sediment measurements including sediment fecal, feed, total organic wastes, total organic waste deposition rate, aerobic and anaerobic biomass, oxygen, CO2, and sulfides. The same external CSV file can also contain data taken from one or more designated pen locations. Available pen data includes ocean current velocity and heading, FCR feed conversion ratio, quantity of feed used, and pen fish biomass, harvest, mortality, weight, growth rate, and pen oxygen and nitrogen levels. When a farm simulation is run, user-selected data from pens and capture cells is output to the CSV file at every time step for the simulation. This farm has been set up to contain Atlantic salmon with physiological growth parameters tuned to Chilean waters. In addition to Chilean-grown Atlantic salmon, AquaModel includes physiological parameters for multiple species or subspecies of commonly farmed finfish, including salmon tuned to northwestern Atlantic waters, striped bass, moi, rainbow trout, cobia, longfin yellowtail, California yellowtail, sea bream, Atlantic cod, Sabah grouper, and lumpfish. By right-clicking, the user can bring up mariculture options, which contains many choices for the user to fine-tune the simulation. Briefly, the Array tab determines the location and size of the model array. The Output tab controls the location of the capture cells. The Pens tab allows the user to set up each individual net pen with species, pen size, stocking density, etc. The Conditions tab allows the user to set some basic environmental parameters. The Operations tab allows for specification of farm operations like feed rates. And the Benthic tab allows specification of some benthic environmental parameters. All of these factors can be modified in greater detail elsewhere as well. AquaModel can also use external data sources that contain time series of environmental data like temperature, oxygen, nitrogen, chlorophyll, salinity, current direction and velocity, as well as time series of farm operations like stocking, mortality, and harvest events, to name a few. These external files allow for much greater detail in setting up and running a simulation, especially when tuning to real-world operations with quality environmental and operational data. By opening the Data Graphics menu and choosing the Plots tab, the user can select one or more of many available plots to view in real time as the simulation runs. We will select nitrogen transect, nitrogen profile, sediment TOC, total biomass, and pen 1 growth rate. The highlighted plots are the ones selected and available to view on the left-hand side of the screen. Pressing OK displays the selected plots on top of the main screen. Many of these plots are transect plots and display a transect of data along the user-selected transect discussed earlier. In contrast, oxygen, nitrogen, phytoplankton, and zooplankton profile plots display data profiles at different depths at a user-specified drill location, shown here as a red dot and modified in the Display tab of the Mariculture Options menu. I will now redraw the transect to lie within the modeled array. By clicking on one of the net pens, the user can pull up a menu that provides real-time data of the pen in question, including statistics like weight and count of the fish, growth rates, temperature and oxygen in the pen, etc. Now, I will use the Simulation Control Options menu to begin the simulation. Once a simulation is run to completion, the user can reload and replay the simulation at will. This includes the ability to save and load multiple different simulations, as well as the ability to jump around in time within a saved simulation. We are now viewing the simulation running at a 30-minute time step, as shown in the bottom right corner of the Simulation Control Options menu. The small arrow in the middle of the array represents current magnitude and direction. The yellow and brown trails leaving each net pen represent fish feed and fecal waste traveling to the bottom. The background is currently set to display false color imagery of nitrogen leaving the pens. A legend for this is shown in the upper right. This nitrogen is a product of fish growth and respiration. You can also see in the pen data window that the growth rate of the fish is positive and that the weight of the fish is increasing. As the simulation starts with relatively small fish, we don't see much effect of nitrogen in the surrounding waters. But if we skip towards the end of the simulation, the fish are now much larger and having more of an effect on the surrounding waters. Similarly, if we go back to the start of the simulation, and look at the sediment total organic carbon TOC plot at left, we see that there is very little elevated TOC at the benthic layer below the farm. Again, this plot shows sediment TOC levels along the transect we drew earlier. We can also go to the Data Graphics menu and select the Images tab to change the displayed background imagery to sediment TOC. This enables us to see a real-time map of sediment effects under the farm. Now, if we again jump ahead to several months in, we can see some small amounts of elevated TOC, both in the background imagery as well as along the transect plot. Parameters like these are critical in determining environmental impact of a farm location. AquaModel is powerful in that we can simulate these effects to determine optimal siting locations, stocking densities, and harvest times. We have now switched to another AquaModel project, also located in Chiloé Bay, Chile, that uses 3D ocean circulation models to provide a far-field view of the region. There are two separate salmon farms in this project, located approximately 6 kilometers apart. As we run the simulation, we can see ocean currents entering and exiting the area from the top left of the array. False color imagery of dissolved nitrogen is shown along with the ocean current fields, allowing the user to observe and visually analyze increased nitrogen dispersal resulting from fish growth and respiration in the pens. The user also has the ability to seed the modeled array with digital drifters that follow the current flows, allowing for trace analyses of circulation patterns as the model runs. On the left side of the screen, we see a variety of user-selected plots. Top left shows a profile of dissolved nitrogen values taken at a designated drill point, shown in red and located in between the top set of net pens. Below that, we see dissolved nitrogen values along the transect drawn across the top pen. Similarly, the next plot down shows sediment TOC levels along the same transect, and the plot at the bottom shows sediment TOC rate of deposition. In the second column of plots, at top we see ocean current flow velocities, followed by fish growth rates and fish weights in a specified net pen. The user has full control to open, close, move, or resize each plot, as well as change the position of the transect and the drill point. The user can also tweak the minimum and maximum displayed imagery values by modifying the appropriate categories in the Mariculture Options menu. Here, in the Conditions tab, we see the chart scale min and max values of displayed dissolved nitrogen, corresponding to the min and max values of the legend at top right. Changing these values immediately changes what is displayed on the main screen. Similarly, the user can modify the imagery color palette by simply right-clicking on the main screen and selecting the palette option. Pressing the Advanced button enables the user to click and drag the various palette posts, shown as black arrows, as well as modify the RGB color values associated with each post. These options are just a few of the unparalleled visualization options for viewing and analyzing a farm simulation available within AquaModel. Full operational instructions for AquaModel are available as a PDF help file when the program is installed. The help file includes walkthroughs for some standard operations, as well as detailed information about every facet of AquaModel. AquaModel support staff is also on hand to help via email, phone, or video conferencing. Please contact us with any questions, or if you are interested in trying out a demonstration version of an AquaModel project. This concludes our demonstration of the Easy AquaModel plugin. Thank you for your time.